Hi everyone, this is Team Swedish Fish, and we're here to present our Sous Vide experiment project. My name is Spencer Flint, and I'm here with my colleagues
Logan Jardine
and Colton Van Wagen.
So this is just an overview of what we're going to talk about. We're going to do an intro, talk about our theory, talk about the modeling, our simulation results, the controller tuning, and then finally we'll have a little discussion and conclusions. So starting with our introduction and objectives, our objective was to design a sous vide. So if you're not familiar with what a sous vide is, essentially it's a French style of cooking meat. So what you do is you take meat and put it in a vacuum sealed bag, put it in a water bath, and then you have this device here that controls the water temperature. We simplified this design, but just so you know how we kind of did it, we took a lacrosse ball to kind of represent our meat so we could have consistent trials. And then we also used a stove top, and our controller output different heating levels. So we used the knob on the stove top to change to control the heater and change the temperature of the water. But we'll get more into that in our theory and results.
So with the theory, one of the most important parts to know is just that it was a cascade controller. So the inner loop was a water temperature controller and the outer loop was a meat temperature controller. So we put in a meat temperature set point, and that went through the primary controller, the error did, and it output a water temperature set point. And then that went to the inner loop and came out and told us what heater percent we needed to set in order to get the right water temperature and then also get the right meat temperature as a result.
Now, in order to put this plan in action, we came up with different models for the water controller and the meat as well. We found that the water was a first order model while the meat was second order, and we did this by performing step tests. And then we were able to use Python code to get optimized parameters for each of the situations. And then we used IMC aggressive tuning correlations for the FOPDT model in order to get PID parameters. And we found tuning correlations from a scholarly article online for the SOPDT parameters to get those PID parameters. And then we were able to use a model in Python to better fine-tune the overall controller.
Awesome. So we'll talk about model and fitting now. So as Logan mentioned, we did a step test for the meat and the water. I won't talk too much about this, but basically, as you can see with the water results here, the response of the water is very immediate, which is typical of a first order response, whereas the meat response is more gradual with that S curve, which is kind of what you'd expect for a second order response. So that kind of showed us that yes, we picked the right models for each portion of the controller.
And also, as Logan mentioned, we used optimization techniques to find our model parameters. You can see the FOPDT fit very well for the water step test, and then the SOPDT also fit well for the meat step test. And we feel like the models represent the actual situation well.
Then using those parameters, we used the IMC tuning correlations shown previously, and we were able to get KC, tau I, and tau D values for the water and the meat controllers. And then from there, we were able to use our models as well as a slide ruler in order to further optimize them. And for our initial test, we used values that were not too far off from those found from the tuning correlations. However, it is important to note that there was slight overshoot, and that's typically something that you want to avoid when you're cooking meat. You don't want the inside meat temperature to reach above a certain point.
Awesome. So we'll talk about our results. So when we use the controller that we designed in the live test, we found that there was significant offset. So on the left, you can see our first controller test. It levels out about 10 degrees lower than the set point. Also important to note here, we decided to use a lower set point, so 45 degrees C. Typically, sous vides cook at 50 to 60 degrees C. So in our controller 2 test on the right, we decided to use more aggressive tuning more aggressive parameters for our controller. And while the results were a little bit better, we still felt like we could improve. So Colton will talk about how we could have improved it.
Yeah, so after some analysis, we realized that the integral term in our PID controller was not accumulating as much as it should have. And we realized that's because when we did the simulated controller, we were doing data points every 10 seconds. But in the physical world, in the real test, we did it every minute. So that meant that the integral term was accumulating 6 times less than it should have. And ways to improve that were to either make the parameters just way more aggressive or re-simulate it, taking data every minute instead of every 10 seconds.
Awesome. Thanks, everyone, for coming out and listening to our presentation. That's it.